go up to H3, you also want to go down to H1. Or you want to show that your solution. So if you have energy greater than or equal to 1, you can show that so in this case we have we go below H1, so all that doesn't show that U is compact in H1 for all time. And then we can use the channels of energy argument of Poincaré and Koenig and Merrill, which says that if you have a compact H1, then you know that outside of some ball R, then you have that small energy, and we actually we can use our radial sublet embedding again to show that the small energy stuff out here has to escape to, have to more or less be dominated by the free solution, and taking advantage of the fact that it's radial means that that you have to, that the only way for that to happen is for this to be equal to a photon for your wave equation. But then, and then you can keep making an argument showing that has to be a photon on the whole R to the 5. But if it's a photon for the whole R to the 5, then it's not an H3 half, because the photon is not an H3 half. So you have a contradiction. In the case of the self-similar solution, you use another argument of Poincaré, Koenig and Merrill, which is to say, so in this case you have again, using like Chris, sort of heuristic of, well, everybody has to work together for a bulk solution. If you have a solution that goes up 5 times, must live inside this light zone. And so then you can reveal that, take W equals then you turn it into a solution that lives in a cylinder. And then you can show you have a monotone quantity, which means you have to have this has to converge to a stationary solution. So then you're just left with solving an elliptic PDE. The elliptic PDE was a little bit more difficult because in the H3 half case, critical case, than it was for if you have a peak higher than 3, I think. So I had to use. So actually, that was an interesting argument because it took me maybe an afternoon to solve this. So then at the end of the day, that you show the solution to your elliptic PDE is 0. And we take advantage of the fact that the solution lies in H2. So we use that extra regularity in this case for the elliptic problem. And it was one of those things where I taught PDEs in the fall, and after I proved it, I realized I had proved it already, in a general setting from something in Taylor's book. And I remembered exactly where I was when I proved it because it was on Halloween night. And so I proved it while watching Children of the Corn. So I don't know, maybe that's why I didn't remember it, I don't know. But, okay, which I recommend the Halloween movie over Children of the Corn, but the original concept 2007 version. So anyway, that's my other literary suggestion too. So lastly, I will talk about one application of our 5D method, and that is to wave map. So if we have a one equivariant wave map, and there are a lot of people in the audience who know a lot more about wave maps than I do. So I will simply, so if we have a one equivariant wave map that maps into, with a target either S3 or H3, then if U is equal to psi over R, U sub TT. So this is a map from R3, a three-dimensional wave map. But when you take U is equal to psi over R, then you pick up a 4 over R, right? So you put it in 5D. So, or it turns into a 5D type problem. Okay. So we have this problem, and so this is the defocusing, this is the focusing. But now let's look at this similar expansion here. cancellation. Oh. You get cancellation in the... Oh, yeah, right. So, and is this 2k plus 1, too? Yeah. Okay, great. So the point is that you get cancellation in the first one, right? And in the third one, you pick up a 8u cubed, and then you've got more terms beyond that. Now, remember, we know that in 5D, we're in 5D now, that you h out to the 3 halves. So we know that, so all these other terms, they might be big, but they're bounded, right? And so we can go ahead and just sum this up term by term, right? But this term here, we treat it just like a cubic problem. And then the other terms, we're going to have r squared, u to the fifth, and so on and so forth. And we can use all those same tools that we have for those problems. We just have to take into it. We're just going to have something, a bound that's going to depend on this norm, right? And of course, if you replace it with a cinch, you do something here with the sign. I don't remember what, but you do something. Probably take it. I don't know. Take it away maybe. And so then you get the same thing. You get the exact same thing because all you're ever doing is just brutally analyzing it term by term. And all those things techniques apply. So that you still get the solution has to be in a more regular state. So you can't use the analysis of energy argument as the elliptic TDE type argument, and so on and so forth. We'll have to stop in our case. So that's about just enough time. So thank you for your attention. Okay. So that's actually, it was nice that this happened, but yeah, it just happened. Everything worked out nicely. But if you take your Morawitz estimate, d by dt of u. So you have your standard. So what? Yeah, because the energy. And now you have to truncate in space, of course, but that's very easy. That's okay because you know that the point is you can go. The point is because you go not only you go h1, but you can get up a little bit above it. As long as you don't go over h with the half. So you can show in the case of energy is exactly 1 that your solution has to be compact h1, not just modular scaling. There is no scaling, it's just compact. So then you take you truncate in space, and that truncation is not going to change your energy too much. It's going to be pretty close to the energy. And you can get these upper bounds on this. You can show that the upper limit of these is bounded by some little o t, where t is the size of your interval, right? And so then you're saying that the integral from 0 to t of this is bounded by little o t. So then the average of your energy goes to 0. Well, the energy is conserved, so then energy has to be 0. In that case, you know that if energy is 0 and you have a solution that's global in one time direction, it must be u equals 0. Okay. So that was really nice. So that in 3 dimensions that worked out. Because we actually tried to do sounds of energy and we couldn't get it, and then we thought, well, maybe crazy. So, well, I'm pretty partial to 3 dimensions myself. So. So we already know the title of our paper, and as Xiaoming already said, the paper consists of mainly 2 parts. One geometric part, proving the equivalence of the 3 curvature conditions, and several different agenda are also added to this part, and an analytic part on the other side, which makes use of the equivalence of these curvature conditions to prove boundedness of the operator, and both parts use entirely different techniques and are also can be read quite separately. So how do I? There's the point. Okay, so this is the structure of my first talk. First, I will give a quick review of what the paper actually says as a whole, and state the curvature conditions once shortly again. And then we set out to prove the equivalence of the first 2 curvature conditions today. So for that we need a few preliminaries, like we need to remind ourselves of the Baker-Campbell-Hausdorff formula, which allows us to compute the composition of 2 exponential maps. And we need to talk about a bit more in detail about the existence of these vector fields coming out of this exponential Taylor type representation that Xiaoming talked about. And we will be patient. And also, since we're already going into details here, it might get a bit dry, so please bear with me. Okay, so let's start with the introduction. So what are we doing here? We're talking about the singular Radan transform.
I chose to write it down without any cutoff and principal values, so as you just see, like, in principle, what object is this? So this should still be familiar from the last talk. I don't think I have to say anything about that. And the theorem that we're trying to prove is that under a certain curvature condition, which comes in three different forms, T and M are bounded operators of LP for P between 1 and infinity. And yes, okay, so these curvature conditions are all local conditions. That is, in our space, R n plus k, which we're working on, we fix a point x 0, 0, and then we are looking at a function gamma which is smooth around in the neighborhood of that point and satisfies the starting condition, so to say, gamma of x0 is everywhere equal to x. Okay, and for the implicit function theorem, then it immediately follows that we can invert this locally in the x variable. So we can find the gamma to the -1, and I mentioned this explicitly so that it's clear that I mean inversion with respect to the x variable only. Okay. Now we repeat the curvature condition Cn again. So the M is chosen because it involves a submanifold M, and for that we need the notion of invariance under gamma to infinite order, which Charmaine talked about already. So I think this is still, it was on the board with many fixtures, so I don't have to talk much about that. And now our curvature condition is that there exists no such invariant submanifold of positive codimension. Okay, and so this is the first theorem that we need to formulate the second curvature conditions, and this is the exponential, the so-called exponential representation of our function gamma. Okay, and I'm always going to use this twiggle, or often going to use this twiggle notation to shorten the notation somewhat, and this actually means that we cut it off at some n and discard the rest as. No, for me T is in RK. So these are multi-indices. Okay. So gamma satisfies this curvature condition if the vector fields x alpha and their iterated commutators span the tangent space of Rn at x0. Okay, and so now we come to the third curvature condition, Tj, J, because it's related to a Jacobian, and it's formulated in terms of iterates of the map gamma. So we start out taking our gamma, and then we put in a second time, and we let it flow again, so to say. This is not the flow, of course, but still, this is a good way maybe to think of this. And we do this n times, so we plug in n different times after each other, and then we look at all the different permutations. All the choices of n time variables. Now we have k times n time variables because each time comes with k variables, and we do this n times. And we choose all the different permutations and always look at the corresponding sub-Jacobian of the Jacobian of our big map capital gamma. And this, if we derive this with respect to some multi-index, it should be non-zero. So this is a sort of a condition on some sort of second order derivative. Okay, so it should remind us immediately of curvature. Okay, now it turns out that these conditions are actually periodic equivalent at each point. And this is what we're wanting to prove. So the first thing that we need is the Baker-Campbell-Hausdorff formula. So as was already mentioned today, one of our main tools is the exponential map of vector field. So how does that work? We have a vector field, and associated with that we have the flow. And now the flow is a function of the time, and we just give this the fancy name exponential map. And this makes sense because it satisfies the semi-group property, and so we have the typical functional equation of the exponential map. And that's where this notation makes a lot of sense, just as a reminder. And it doesn't hurt. But yeah, this is a one-dimensional time. Just, here we have a-dimensional time. So it doesn't hurt if you think of these vector fields just as maps from Rn to Rn. Yeah, so we have a bunch of vector fields, and another bunch of vector fields, and we form these linear combinations. And now we would like to know what is the product of these exponential maps. So yeah, I actually didn't tell you how do we interpret an exponential map if we plug in a time vector, but this works in the same way. We just plug in the linear combination as a vector field, and we let it run in a one-dimensional time, and then stop it at time 1, t equals 1. And then this gives us our exponential of the linear combination of the vector field. Okay. And now this Baker-Campbell-Hausdorff formula is actually a very algebraic thing. It doesn't have to do anything with analysis. It can be formulated just in terms of formal power series. Right? So, but here we need it in an analysis form, so I have given the formulation in terms of local diffeomorphism. So that's why we need this additional overflow. We're not talking about formal power series, but actually nothing much is happening here. So what this says is that we get an exponential of this ugly expression, and the ck are Lie polynomials homogeneous of degree k. So what's a Lie polynomial? That's a finite linear combination of iterated commutators. Okay, and it's homogeneous means that it contains only one type of commutator, so one number of commutators. So it will also be homogeneous in the usual sense. Okay, and so now we would like to know what are the first few terms. This is normally not interesting what is C10 or so. This is, you can compute it, but it's not going to give you much insight. But the first few are maybe interesting. So C1 is just the sum, what we would expect from the case where they commute, the vector field, because this is just a functional equation. And C2 is then the commutator, and C3 already gets weird. Okay. So this is the Baker-Campbell-Hausdorff formula. And now our theorem, which was already on the board, which we would now like to prove, at least a part of it, is that given gamma, as before, defined in the neighborhood of some x0, 0, smooth, and satisfying gamma x0 equal to x everywhere, we can extract these vector fields from it such that this exponential representation holds true. We will only prove existence, and I hope that you will believe these are uniqueness. Because the uniqueness is essentially a calculation, and it's the existence, but we need the details of this calculation because they will later be relevant for the proof of equivalence. Okay, so what's the idea? The idea is we would like to get some kind of flow such that we can extract from that a vector field. And so our gamma is not a flow. So we would like to write down the flow. So how do we start? We start by defining this h. Okay, essentially just taking gamma and adding the time in the second component. And we can compute the Jacobian to see that this is a diffeomorphism of a small neighborhood of x0, 0 into another neighborhood of that form, because gamma x0 always goes into the identity at time 0. And t equals to 0. Okay, and so in that second neighborhood, we will from now use the coordinates ys. And for small s, we now define something that should be a flow, from which we will then extract some vector field. Okay, and so how do we define this? Ys is just, u2 is, y is in Rn and s is in Rk. U1 under h. They're actually supposed to be the coordinates. So maybe I didn't quite write it down very well. Yeah, sorry about that. So we define the flow. Well, I would. Okay. So if we write it down like this, it is a flow by definition, right? Because we put it's evident from the definition that it's true. What? No, h doesn't equal t. Yes, this is, I said already, I wrote this down wrongly. You should ignore this line here. This line which I'm right now highlighting, you should ignore this. Yes, please ignore this line, which is right now highlighted. Right? We don't define y. What? Yes, exactly. I just wanted to say that ys is... Yes, ys doesn't exist yet. I just wanted to fix the notation for the coordinates in the second neighborhood. And so I was thinking that it is the image, but it is not, okay? Because then, as Pascal already said, of course, t would be equal to s. So there's no sense. T is not equal to s, okay? This is a typo. Okay. Well, this phi s makes out of this gamma a flow. It is built such that the semigroup property is true. Because the way it involves s is just linearly, so if we plug in s plus s1 plus s2, it will just come out as a composition of phi s1 and phi s2. I can do the calculation maybe. Or I hope so.